This is my Physics 2211 Lab 2 on projectile motion. So just a brief overview, we're going to go into introduction and purpose, the concepts that go behind this, the experiment itself, some of the coding, and the comparison and errors and what ifs. So just a brief introduction and purpose. The purpose of this lab was to compare an actual object's projectile motion to a calculated projectile motion with coding. And so we did this by doing Tracker, which is an application used to track an object, and then GlowScript, which is our coding with Python, and other resources. So some of the main concepts in this lab is Newton's momentum principle. So it's just the change of momentum over a change in time, which is equivalent to net force. And then force of gravity, because that's involved in this object's motion. So it's pulling down on the object at a force of mg. And then drag force, which you'll see a little bit later, but we don't talk about it really much in the class, but it is something that is kind of, I guess, relevant to like air resistance. And then lastly, velocity and position update formulas. So VF is equal to VI plus F net over M times delta T. So that's F, that's looking for a new final velocity. And then what we're doing here is we're looking for another position once you get that velocity. So the experiment itself was actually recording an object in its motion. Then we track using that app, like I said, and then we're later going to use GlowScript to code expected data and results, and then compare those findings. So some of the experiments, the results, or just like an introduction to the experiment itself, I guess. The surroundings were earth and air, I guess like air resistance. So that's like kind of where the drag comes into it. And then initial conditions that we set were 0, 0, 0. And then we said that the mass of the paper ball is 5 grams, or like really small. So this is the video. As you can see, it's really quick, but it does go in like a parabolic motion right here. So we'll look a little bit into that later. So as you can see here, we do have the little red points on the right. You can see like the where we were tracking that ball, and that's equivalent as to what you see on the left. So that's tracking its Y and X position. So this specifically is a Y position. So you can see this little parabolic curve. And so it didn't start exactly at 0, 0, 0 on here, but it does later, but it doesn't start at 0, 0, 0. But we like kind of said it would, but according to the tracking, it starts at 1.8. So it does go higher. And so in theory, it should stop at that like 0.325 second area, but it goes a little bit longer as we drag it out. And then some of the observations is that we noticed it was in the air for about 4/10 of a second. We tracked that the total X distance that it traveled, that horizontal distance, was equal to a meter and some change. And then the max height it reached was actually 0.3828 meters according to the tracker. So we did a not initial velocity. So we calculated using those first 2 time steps in the tracker. And this is also what we're going to use for the initial conditions in the code. So it's just a little bit of math here. It's just taking that first X position minus the second X position minus the first X position, and then the second Y minus the first Y, and then change in time of those 2 intervals, and then you got 2 initial velocities. And so when we come to the actual coding, we can see here, we can go line for line. The mass is 0.005 kilograms, which is equivalent to 5 grams. And then some of those initial conditions, as I was mentioning earlier, the ball position, we use 0.1800 meters. So like I said, the tracker did say that it started at 0.18 meters. So we just went ahead and plugged that in just so that we wouldn't mess anything up and try to keep those results, I guess, similar. And then the velocity, like I said, was calculated from that previous slide, and that's what we used. And then what we're doing here with these lines is we're saying T is 0, and then we're going to change it by hundredths of a second, or a thousandth of a second per like interval, and it's going to keep going. And then we have gravity is 9.8, and then this was our drag force. So our lab TA actually just helped us out and said that this is what we would get, and this is the value we should be using to use that. So yeah, to continue upon that, what this line of coding here is doing is while T is less than 0.4, so it's just maxing it out at 0.4. It's going to stop at 0.4. We're going to continue. We're going to continue to look at the net force here. So the net force is, or the F of G is the vec at just the H position. So it's the ball of the mass, so minus mg, because it's going downward. And then the drag force was minus b, which was the coefficient of drag, which we said was like 0.13 earlier. And then the magnitude of the ball's velocity. So that's that. And then the net force was the force of gravity times the force of drag. So it's just combining those to make a net force. And then lastly, we applied the velocity update formula and the ball position update formula. So we said that the initial velocity plus the net force of the ball, which was fg plus f drag, over the mass of the ball times delta t, is going to give us that new final velocity. And then we're going to use that in our positions update to find the new position. And so some of those coding results, as you can see, it kind of looks pretty similar to what we had on the tracker. So like I said, we set the initial to 0.180 for the initial height of the Y position. And so as you can see, over time, as it hit that 0.4 seconds, it did continue to have that parabolic shape. And then we look at the X, it was a little less linear than we thought it should be. But I mean, then again, it's coding. It should be more accurate theoretically, but, might just be error somewhere. And so like I said, lastly, some errors. There could have been human error from our positioning and whatnot. So we could have messed up somewhere in the coding or somewhere in the actual experiment itself. And then secondly, we probably had improper framing and structure when it came to recording our video. So when we recorded the video, the framing of like the meter stick with the ball might have not been as accurate as it could have been. So that's definitely going to impact the experiment. And then finally, the technology error. So maybe, when we were recording the video, we might have, I don't know, cut out a frame that could have helped us out, or when coding, we might have messed up somewhere. So yeah. And then just a final slide about like what could have happened. So what if there was 0 gravity? what that would do is that there would not be a parabola of motion. So like how we saw the parabola of motion with the y direction, we would just see that it would move in a straight line since the vertical acceleration would be zero, since there's no negative 9.8. And then secondly, what if the object was launched straight up? What that would do is there would be no horizontal movement. So there would be no horizontal acceleration, no horizontal velocity. And so when we look at the graph, it would just be up and down of the y position. And we would only see, like I said, displacement of y, and we would see it fall up or rise up and then see it hit some max height and then see it fall back down. Thank you.